actually is covered by an area that have 50 millimeter per year. And this actually make a pressure in the water resources limitations in Jordan in general. So there is a water problem in Jordan, and this water problem is divided in two parts. First of all, that there is limited water resources. So the rivers and the lakes and the groundwater level in general are low in Jordan. And the second part is because of the high population growth, which reaches to about 3% per year, in addition to the high number of refugees that come to Jordan during the last 10 years. And therefore, we need a sustainable management for the water resources in Jordan. And this sustainable management led us to think about using the wastewater as a resource for water for irrigations or for industrial activities. The wastewater is come to Jordan from different wastewater treatment plants, and actually we merged it with different rivers in Jordan. And the objective of the research is to evaluate the effect of this mixing in the surface water flow that we have. Two case studies were chosen, the King Talal Dam and the Ziqlab dams. King Talal Dam is the biggest dam in Jordan. It's earth-fill dam and has a capacity of about 85 million cubic meter per year. The main river that supplies this dam by water is the Zarqa River. It has a base flow of about 33 million cubic meter per year, and a flood flow about 37 million cubic meter per year. The second case study is the Ziqlab Dam. It has about 8.3 million cubic meter per year as a base flow, and 2.2 million cubic meter per year as flood flow. What is Ziqlab Dam has a catchment area of about 106 square kilometer. It's extended from the highlands in the west of Jordan to the Jordan Valley, and could store about 5 million cubic meter per year. So now these two dams receive surface water from two different rivers, and these rivers receive wastewater treatment water. The objective, as I said, is to evaluate the effect of this mixing in the water quality of the dams. Several samples were collected from these two case studies, from the wadis area, from the streams that supply the dams by the water, and from the water body of the dam itself. Also, we used data that about the King Talal Dam were collected from different resources, and of course from the Ministry of Water and Irrigations. Now, the major factor that we used to evaluate the water quality was the EC value. As we know, the EC value represents the total dissolved solid in the water as a general description. And here we could see that the stream EC value in the both dam is higher than the EC value of the water in the dam itself. And this make the mixing actually destroyed or degrade the water quality of the dams, especially for the King Talal Dam that we could see this differences in the EC value, obviously. Also, we observed different concentrations for different ions. For example, for the nitrate, we could see that the value of the nitrate in the Zarqa River is much higher than the nitrate value in the dam itself. Also, for the potassium and calcium, we could think about the nitrate and potassium from the fertilizers that in the soils maybe could reach to the water by the irrigations, and also from the different factors in the catchment area of the Zarqa River itself. So obviously for us here that the water quality of the Zarqa River is less than the water quality of the dam itself, and the mixing led to degrade the water quality in the dam, as I said. For Ziqlab Dam, the case study maybe is in the opposite directions. The water quality maybe in the dam, it's not much better than the surface water that supply the dam itself. But as I said, in the King Talal Dam, the differences between the water qualities was obvious for us. We novel costs diagram that we use it for the sodium saline hazards. We try to plot the water qualities in this diagram of the two dams, and we could see that the both dams, Ziqlab Dam and King Talal Dam, locate within the low salinity hazard for this diagram. So this encourages us to think that the water quality in the both dams is suitable for irrigations, of course, more than the other uses. There is a factor called Kelly ratio factor, and this factor is actually represent the ion concentrations of the sodium over the calcium plus magnesium. And the idea was to evaluate which dam of these two dams were affected by the mixing more than the other. Here we could see that the mixing affect the water quality of King Talal Dam more than the Ziqlab Dam. And it's also proof for us that the water in the both dams is suitable for irrigations more than the drinking uses. So as a conclusion and recommendations, we could see that the mixing wastewater treatment or the treated wastewater always increase the pollutions in the surface water of the both dams and make degradations for the water quality usually, and therefore the waters in the dams in Jordan actually is suitable for irrigation purposes more than the drinking usages. And if we want to make better management for the surface water in Jordan, we could think about make dams for treated wastewater and other dams for the base and the flood flow waters. Thank you so much for your attention.
Thank you, Dr. Taleb, for your good presentations, and I think very, very useful for us to hear this presentation from your experience in the two main dams in the Jordan Valley. Now the next presentation will be from Oman experience, and our next speaker will be Dr. Kassim Al-Jabri, and he will present the new, I think, as he told me in the morning today, from his PhD, will be this brief about his PhD about the assessing of the resilience of water supply system in Oman. Dr. Kassim Al-Jabri, let me give a brief about his CV. He's working in as a senior manager project support a public authority of electricity and water, Muscat, Sultanate of Oman. He enjoyed the Ministry of Housing, Electricity and Water in July in 1987. And he has more than 25 years of experience in the operations and maintenance and design of water systems. He has a member of the technical papers in the field of water. Please, Dr. Kassim.
Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you for being here my presentation is entitled Assessing the Resilience of Water Supply System in Oman. The agenda of my presentation will be explaining the problem statement, aim and objective, research methodology, result of risk assessment, evaluation of resilience, discussion, and then conclusion. The problem, water supply system in Oman are exposed to a range of risk, natural and man-made. The location of Oman on the northern Indian Ocean and Arabian Sea is in the tropical cyclone zone, is subjected to hazard, storm, and cyclones. So Gono in 2007, in June 2007, severe category 4 cyclone Gono hit Oman with 213 to 232 kilometer wind and heavy rain and surface runoff, causing substantial damage to the critical facilities of water. So there are also some risks arise from the operational practices, for example, non-revenue of water, which is one of the major challenge facing water utility management worldwide and Oman as well. So this research developed an integrated approach to identify and rank the risk and recommended methods of analysis and assessment to improve the resilience of water supply system in Oman. Actually, this is part of my PhD, which I cannot maybe summarize it in 10 minutes. So I try to touch the flavor of the PhD and present it to you. So this was my aim and objectives, to bring an understanding of how resilient to various hazards, natural and man-made, in water supply system can be developed in the Sultanate of Oman, to develop an integrated approach to identify and rank risk and recommend method of analysis and assessment to improve the resilience of water supply system in Oman. The objective was to assess the resilience of water supply system in Oman through analyzing and assessment of risk, including desalination plant, transmission pipeline, and water distribution network, to determine how these risks can be reduced through effective management measure of mitigation. So this is my research methodology. I cannot go through all because this is covering all my PhD, but to meet the aim and objective of my study, I start with the data collection. Then I call for a workshop from different experienced people which is within the public authority, from the desalination plant, from water network, and from water quality. I make some, it's not clear here, it's very small. Writing is
واضحة فوق. أنت مش واضحة لك؟ هي واضحة للناس.
هناك بس أنا يعني
قرب عليها نظاراتك نفسها.
لا هي الكتابة صغيرة جدا. ما مشكلة. Okay. And then I made a questionnaire to the senior people, also make an interview to other people within the ministry, within the public authority for electricity and water. And then I make identification of hazard. This, in the workshop, we are divided in the 3 groups. One group will look for the desalination plant, and then the other with the water distribution network, and the other group with water quality, to assign and identify the risk affecting these 3 disciplines. So in desalination plant, we have looked to the risk from the sea to the desalination plant. And within network, we look for the pipeline and reservoir, and then in the water quality, how these risks affect the water quality. So in risk assessment, due to the lack of adequate information, semi-quantitative risk assessment approach, namely coarse risk analysis, which called between brackets CRA, used to analyze and assess of risk for water supply system in Oman. The scope of the CRA consists of identifying hazard event related to the water supply system, estimate the probability and consequence of each hazard event, ranking the hazard event with respect to their risk, and determine risk, which as risk equal to likelihood multiplied by consequence, assessing the need of risk reduction option. All this has been discussed in the workshop, and we agreed to use this approach or this methodology, that CRA, to identify all the risk. The coming slide will be showing the result of this workshop and interviews and so we can say risk factor were identified, ranked, and scored at stakeholder workshop, which as already I mentioned. CRA is presenting probability as rare, unlikely, possible, likely, and certain, and consequence as a major, minor, and severity. The combined category are inserted in a risk matrix, shows numeric description of risk ratings, which is, I am going to present it now. So we have here three. This table is the outcome of the workshop to agreed on how these risks can be scored and how can be managed. So the first table on left, it's a quantitative measure of the likelihood. So there's a five level, and we have a 5 score. So for example, if we go for the level 1, it's this event, it may happen 1 in 50 to 200 years. So we gave the score is 1. But if we came to the number 5, it's more than 1 per year, which is, it's coming frequently, so the scoring will be 5. Then we did the consequence for each event during for desalination plant. And this is, severity is A, B, C, D, E, and then we are putting the score as 1 to 16. For example, if we go for the category A, that 12 hours partial reduction of treated water production. We gave it 1 because within the 12 hours we can retain the system or the treatment work, the desalination plant to work. But if we go to severity A, people will stay 7 days without water, with loss of water. So we rank it as a 16 because it is very high. At the same time, we do the consequence for the event of the transmission main. And the same, if you find the A severity, you will see 500 property without water for 12 hours, which is 1. And then if we go to E, it is about 100,000 property without water for 12 hours is more than, and then we give it to 16. These all developed the risk matrix table. So we have the level of likelihood 1 to 5. Then we have the severity is from A to E. And then we define the risk. So if we go like green, it's minor. And this definition of green, minor severity is above 6, representing minor risk that may not need any mitigation measure. If we get to amber, it is really, I cannot read it because my glass is not, writing is very small. Maybe it's clear to the audience. If we go to C, to red, it is, red is severe. So that 16% significant risk that certainly need mitigation measure. From that, we come to the result of risk assessment. This is a summary because there is another table which I cannot present it here. So I bring the summary of the risk to Al-Jabri desalination plant, which is one of the main desalination plant which is supplying water to the capital area, Muscat. So we can see here the L and C, which is likelihood and consequence, which is applied together. That time 3 times 16, it comes to risk is about 48. So this is a summary, but there is in detail in the PhD. So like if we go for the jellyfish, we find that the likelihood is 2. C is 16, so it's 32. This is before control, and this is the after control. We can see that from when we apply the control measure, we reduce the severity of risk from red to amber, and as follow for the others. This is the summary of risk for Greater Muscat water supply system, which is for the transmission pipe, transmission main, pumping station, and loss of supply from desalination plant. And it is the same what I have used in the, oops, too fast. Interpretation of risk. I summarized that, the severity of risk, the number of severity risk to water supply utility. If we go for Al-Jabri desalination plant, we find that seawater quality is before mitigation is 5, and and after mitigation, it rose to 4. And if we go to Greater Muscat water supply system, transmission is reduced from 4 to 3, and from 6 to 3. I have to go very fast since time is, this is evaluation of risk. Translating of risk score to level of resilience. So this is the risk factor is 1 to 5, its level of resilience in 4, and resilience ranking will be very high. And 6 to 15, 3. So I will go to this, so we convert the level of resilience for Greater Muscat water supply system. So we put the ranking and the scoring of the resilience. We can see with the transmission main, the resilience was 1, which is low, and after mitigation is increased, it comes 2.3. 2.3, that's moderate. And then for pump station, the resilience is improved from 1 to 2.3. So the average resilience score for water supply utility, we can see here from Al-Jabri, and before control it was 23, and it goes 2.3, and it goes to 2.7, and then from 2.2 to 2.8, and for Greater Muscat for transmission also, the increase